All right, I want to go now to section 4.3, part 1, video. And what we're going to look at in this particular section, we're about to turn and just go in a completely different direction. And you'll see why once we get there. If you'll remember, at the very end of the last section, I put up an exponential problem, and it was this. If you remember when we tried to work that, we saw that we could not work that problem, that we could not solve this exponential equation because there's no common base. But I told you, I said, this problem does have an answer. It doesn't have a whole number answer, but it has an answer. And we're going to learn how to solve this. But we're going to have to solve this by using a different technique other than what we looked at in the last section. Why? Because these two numbers, 2 and 27, they do not have a common base. You can't write 27 and 2 as an exponent using the same base. It's not possible, like we did in the other four. So I told you we would revisit this problem. The reason we have to revisit it is this is what you're going to have to use to work this problem. We're going to have to use logarithms to work that problem. And you say, what on earth is that? That's why we have to have this discussion. So the next 3 or 4 videos is basically going to be talking all about logarithms. And when we get through this whole section, when we get into the next section, that will be the very first problem that you and I work together in section 4.5. So the purpose in 4.3 is to give you way more information than you probably want to know about logarithms. But we have to do that in order to work the problems in 4.5. There's also another problem in 4.5 that we're going to need to work, and we're going to use logarithms also. So that's why we're having the logarithm discussion now. Okay, and we're going to creep into this. I'm going to assume that until right now you've never heard of this word a day in your life. And I'm going to make it as simple as I possibly can. Okay. First of all, but it's very important that you take good notes and you pay attention to the lecture and you write things down that I tell you to write down. First of all, probably somewhere on your scientific calculator, you have seen this button right there on your calculator. That LOG is short for the word logarithm. Now, there's actually 2 kinds of logarithms on your calculator. There's another kind of logarithm. It's this one. This one right here is what we call a common logarithm. This one is called a natural logarithm. Now, let me tell you this first. I'm going to talk a little bit about this, but there's no homework with the natural logarithms, so I'm not going to labor there long. All of your homework is dealing with the common logarithm. But just to show you, I think I have it here on my calculator. I do. How well you can see this. This right here is LOG. That right there is LN. This is a common logarithm. This is a natural logarithm. I'll talk about the differences in a minute, even though you don't necessarily need them for this course. All right, so before I do that, I want to talk about what is a log. So, if you have your calculator, let's do this together. If you don't have your calculator, pause the video now and get your calculator. Okay, now what I want you to do is I want you to take your calculator and take the log of 1,000 and hit equal. Now, some calculators you may have to punch in the 1,000 first and then hit log. But most calculators you punch in log, it'll put a parentheses, put 1,000 and close the parentheses and hit your equal. All right, when you do that, this is the answer you should get. Now, what I want to do in just a minute is I want to talk about where that 3 comes from. Because in just a minute, you're going to do some of these logarithms without a calculator. But right now, I just wanted to make sure you punched it in and you got an answer of 3. But I'm going to show you how to do it without a calculator in a second. In order for me to show you that, there's a couple of things you need to understand about a logarithm. This part of the logarithm we give a name called the argument. That 1,000 there is called the argument. But there's another number over here, and you say, well, I don't see another number. That's because it's understood. There's a little bitty number that goes right here, but it's not written. That little bitty number right there, so the number that goes here is called the argument. This little bitty number that goes right here is what we call the base. Now, if there is no base written, it's understood 10. So when I read this right here, let me show you how it's read. The log of 1,000 base 10. So if there is no base written, it's understood 10. Now, is the base always 10? No. So if the base is anything other than 10, you have to put it. So the base doesn't have to be 10 every time. However, your calculator only operates in base 10. So most scientific calculators, if I wrote this, most calculators cannot calculate that. Now, if you've had some other mathematics, there's other ways to do this, but your calculator won't give you an answer for this one because you're operating in base 2. Now, it gave you the answer for this one because you're operating in base 10. We'll come back to that in just a minute. So, let's talk then about where does that 3 right there come from. So let's write this problem back down again. Okay, let me ask the question that I've already said 2 or 3 times. What is the base in this problem right here? The base is 10. Now, anytime you use the word base, there's another word that is always associated with it that you typically hear that goes directly along with it. Just like if you've ever, it's a silly example, but if you've ever ran into 2 people, every time you see one, you see the other. So whenever you mention one of them's name, you may as well be talking about both of them because they're always together. Well, the word base is always tied together with the word exponent. You got a base and you got an exponent. Now, let me show you where the 3 comes from. Here's what this problem is asking. If you use base 10, what exponent on 10 would you have to use to get that 1,000? That's what we're looking for. If you use base 10, what exponent would you have to use to get the 1,000? Well, it would be 3. That's where that 3 comes from. So that's how that is worked. Okay. Now, I will show you why in just a few minutes, but let me talk about this argument in base for just a second longer. Argument Remember I told you the base doesn't have to always be 10. It can be anything. It turns out that your argument and base can't just be any old numbers. They're limited some. Let me tell you what they are. When you're dealing with logarithms, the argument has to always be greater than 0. Or another way to say that is the argument has to be positive. Now, notice I did not say it could be equal 0. So, you cannot take the log of 0. If you don't believe that, take your calculator. If you've still got it in your hand, punch in the log of 0, hit your equal key, and it'll give you an error. The argument can't be negative. You don't believe me? Take your calculator, take the log of -5, and hit your equal key, and it will give you an error. So this number right here, your argument, what you're taking the log of, has to always be a positive number. Now, it doesn't have to be a whole number. This number right here could be 7.3, 15.2, 89.476. It could be anything as long as it's bigger than 0. Now, we typically are not going to deal with where it's decimals. We won't. But still, as long as it's positive, that's the only stipulation. Now, there's also a stipulation on the base. The base has to be greater than 0 also. But there's one extra. Stipulation is that the base can never be 1. So this has got to be positive, this has got to be positive, but this right here can never be 1. I'm going to show you why that's the case on some of these in just a few minutes. So, let me just remind you something. Remember that pi from geometry is 3.14. So could your argument be pi? Yes. Are we going to ever work it where the argument is pi? No, we're not. But it could be, because pi is a positive number. Could the base be pi? Yes. Now, let me mention a number that you may or may not have ever heard of. And this is approximately. The number e, which again you may or may not have ever heard of in your life. E is about 2.72. The number pi is used a lot in geometry formulas. The number e is used a lot in banking and the financing world. Business banking, financing. That's where that number e is used a lot. When you are buying a house or doing something like that, the number E is in a lot of those formulas when you're dealing with those. Doing certain things involving interest and stuff like that we're not going to do, but that's where that number E is used a lot. So, can this be E? Yes. Can this be E? Yes. Here's the reason I'm saying all of this. Anytime your base is E, that is the same as that. So, let me give you an example. If I ask you to punch this in with your calculator, you can punch this in with your calculator. And the reason you can punch this in with your calculator is what's this base understood to be right here. This is understood to be base 10. All right, punch this in with your calculator. Take the log of 10,000. When you do, you're going to get 4. Why? Because the base is 10. If you take 10 to the 4th power, you get 10,000. So this is true because of that. Now, if I ask you to punch this in, you say, well, I can't punch this in because this is base E. That is true. But I just told you that the log base E is the same thing as that LN button on the calculator. So this would be the same. You don't have to put the parentheses. So if I ask you to punch this in with your calculator, it's the same as using the 10,000 and using that LN button. You don't have to do that. I just want you to see where that comes from. So the LN is the logarithm when it's base E. The LOG is the logarithm when it's base 10. So if we're operating base 10, we can always use LOG. If we're operating base E, we could use LN. That's where that common logarithm comes from. Now again, we're not going to be dealing with this. So with this LN, I just wanted to roll that out there for you in case you run into that, and maybe if you're taking business calculus a little bit later on. But we're going to limit our discussions to the common logarithm, LOG. So from this point on, anytime I say logarithm for us, I mean common logarithm, which is LOG. All right, so this right here. Why is the log of 8 base 2 equal to 3? Why is that true? Because if you take 2 to the third power, you get 8. So this is true because base 2 raised to the third power equals 8. This is what we call the log form of the equation. This is called the exponent form of the equation. So, if I give you the log form, you ought to be able to convert it to the exponent form. And vice versa. If I give you the exponent form of the equation, you should be able to write the log form of the equation. That's real easy to do. All right, so let's do a few of those. Write these instructions down. Convert the following to the exponent form. Convert the following to the exponent form of the equation. Okay, pause the video and copy these 3 down. Okay, I'm assuming you've copied these 3 down. Now, we're not working these out. I'm not asking you to work this. I'm giving you the answer. So there's nothing to do here. All I'm wanting you to do is convert it to exponent form. So this is a true statement. All right, so if you convert it, what's the base? 10. Your answer is your exponent, 4, and that should equal 10,000. So if you convert this to exponent form, let me see if you can see that over there. Yes, you can. If you convert that, it would be 10 to the 4th equals to 10,000. You say, well, what if I get these numbers over here in the wrong place? You won't, because if you get them in the wrong place, it won't be a true statement. And that's certainly a true statement. Okay, so let's do this one. Here's your base, 4/5. That's your exponent, and it's equal to 25 over 16. Now let me say again. This right here, the way you know you got the numbers in the right place is this is a true statement. What does the negative do? It flips your answer. So what is 4 over 5 squared? 4 squared is 16. 5 squared is 25. So that's 16 over 25. But the negative flips it. So that's a true statement. Now, how would I rewrite this one? It would be b, that's your base, to the c power, that's your exponent, equals, and then a. So we're converting from the log equation to the exponent form of it. So these two statements are the same thing. You're going to see why later on the converting is important. All right, now here's what I want to do. I want to give you some exponent problems, and we're going to convert it back to log form. All right, so write these instructions down. Convert the following to the log form of the equation. Convert the following to the log form of the equation. Okay? Here's the three problems. 4 to the negative 3 power equals 1 over 64. And that's certainly a true statement. Okay, come over here, write down log. 4 is your base, so that's the little bitty number. Negative 3 is your exponent, that goes on the other side of the equal. And then the 1 over 64. So when you write this, log, your base is 4, it goes here. Your exponent goes over here, equals, and then what's left goes right there. Now you can always double check it. This to this power equal that. All right, so let's do this one. Log (100) base 10, base is 10, exponent is 2, and 100 goes there. Now remember, it wouldn't be anything wrong if you left the 10 off. And then the last one, base goes down here, exponent goes over here, and what's left goes right there. So that's how you convert from a log equation to an exponent equation, and from an exponent equation back to a log equation. All right, we'll stop here. We'll pick up with video 2 next.